lab for determining the proportionality constant R in the ideal gas equation. Purpose of today's lab is to employ the ideal gas law and Dalton's law of partial pressures to determine the gas constant R based on oxygen gas produced in the following reaction. Hydrogen peroxide decomposes to form water and oxygen. So 2 moles of hydrogen peroxide decompose to form 2 moles of water and 1 mole of O2 gas. Should look familiar to you. You've probably seen this in lecture, the ideal gas law. PV equals nRT, where pressure is the pressure of the gas in atmospheres. Volume is the volume of the gas in liters. N is the number of moles of gas in moles. T is the temperature of the gas in Kelvin. And R is the gas constant, with units of liters times atmospheres divided by moles times Kelvin. First, let's talk a bit about vapor pressure. This will be important for this lab. So some molecules at the surface of a sample of a liquid have enough kinetic energy to enter the vapor phase, even if the liquid is not boiling. Therefore, a glass of water left open will eventually completely evaporate. This is an example of vapor pressure, the magnitude of which depends on the temperature of the liquid. As the temperature goes up, the vapor pressure also goes up. And why is that important to experiments like the one we're doing today? So often, like you'll be doing today, you're collecting gases over water. And when you're doing that, you're going to have to take into account both the pressure of the gas that's produced. In the example that I'm showing here, we have zinc reacting with hydrochloric acid to make hydrogen gas. We have the pressure of the hydrogen gas plus the pressure of the water vapor. Those two together will be equal to the atmospheric pressure of the room. Gaseous products of reactions are often measured by the displacement of water in this type of setup. The pressure of the gas inside the collection tube is the sum of the pressures of the product gas and of the water. The total pressure is equal to the partial pressure of the product plus the partial pressure of water. If you know the total pressure, and it's usually atmospheric pressure, and in the experiment you're doing today, that's what it is. The total pressure is atmospheric pressure, and you know the partial pressure of the water, you can find the partial pressure of the product. Let's talk about a manometer before we get into our particular experimental setup today. So a manometer looks like this, where we have one end of this tube is open, and we have a gas on the inside here. And in this particular setup, as shown here, the pressure, atmospheric pressure, is greater than the pressure of the gas. How can I tell that? Because the two columns are unequal. Because the atmospheric pressure can push down harder than the gas can push down, the mercury gets pushed up on this side. In this setup, we have the pressure of the gas is larger than the atmospheric pressure. And how can I tell that? Because the column on the atmospheric pressure side is higher than the gas sample side. Because the atmospheric gas can press down harder than the atmospheric pressure is pushing down, and so the mercury column goes up on the right. If the level of the mercury in each side of the tube were the same, the trapped gas would be at the same pressure as the atmospheric pressure. In our setup today, you're using deionized water rather than mercury, and you can manually adjust the water level by moving the leveling bulb up or down as the reaction proceeds. So here is the particular calculations that we'll be doing today. Once I've shown this entire slide, you may want to take a photo of this particular slide or ask your lab assistant to stop it here to give you time to do that. So we have our PV equals nRT again here, but I put in a little bit more detail. So it's the pressure of what? The pressure of the O2 gas. The volume that the gas is contained in is equal to the number of moles of O2 gas times the gas constant R times the temperature of the gas in Kelvin. From your experimental setup, you will obtain the volume of O2 gas produced. So once you've got your leveling bulb level with the volume of gas, that is your measured volume of gas that you have. Using this value, the atmospheric pressure, the temperature of the water in the leveling bulb, and the vapor pressure of water at that temperature, you can calculate the total number of moles of, this should say O2, sorry, O2 gas, to figure out your desired value for R. So here's a little bit more data on how to get each one of those pieces. So the pressure of the O2 gas is equal to the atmospheric pressure minus the vapor pressure of the H2O. Vapor pressure of the H2O, you'll figure out based on the temperature of the water in the leveling bulb. You'll look up in the table in the experiment, and you will find out what the vapor pressure of the water is. So total pressure minus the vapor pressure of the water will give you the pressure of the O2 gas. Volume, you've measured that by displacement of water. So you'll measure that directly from your burette, and you'll convert that into liters. The temperature will be the temperature of the water. You will measure it in degrees Celsius. You will want to add 273.15 to your measured temperature to convert it to Kelvin. The number of moles of O2 will be calculated from the mass of H2O2 that you used. Because for every 2 moles of H2O2 that decompose, you form 1 mole of O2 gas. Okay, and so here is where lab instructors could please stop and let the students either write this down or take a photo of this if they want to. So things to remember and watch out for this experiment. Record today's barometric pressure from the board. Your lab assistant should put that on the board. Only read the volume on the burette when the level is even with the leveling bulb. If they're not even, you want to move the leveling bulb until the level in the burette and the level in the leveling bulb are equal level. Determine the vapor pressure of water at appropriate temperature and account for this in the measured pressure change. So measure the temperature of the water bath, look up in the table the vapor pressure of water at that temperature, subtract that from your atmospheric pressure. You're going to coat a small stir bar with petroleum jelly and then roll it in yeast. Shake it to confirm that all of the yeast is adhering to the stir bar. This yeast is your catalyst for the reaction. It causes the breakdown of the hydrogen peroxide to happen rapidly. Before connecting the Erlenmeyer with a sample, adjust the burette and leveling bulb so that the burette reads somewhere between 0 and 5 mLs, and the leveling bulb is only 2 to 3 centimeters full. Otherwise, you run the risk of overflowing the leveling bulb or emptying the burette. Measure the temperature of the water in the leveling bulb at the end. One partner should use the large stir bar to hold the small stir bar above the surface of the H2O2 solution, while the other partner seals the system. Use the large stir bar to move the small stir bar, stirring the H2O2 solution. And here's a glimpse of our setup. So we have, this is where our reaction is going to take place in this large test tube. This is the beginning, and right here we have our small stir bar coated with petroleum jelly and yeast. So one of you would want to use the larger stir bar to hold this in place, while the other makes this final seal and adjusts the leveling bulb and all that if you need to, so that the levels are equal. Then, once you are satisfied that that's true, you don't want to drop it because it is possible to break the bottom out. You want to use the large stir bar to slowly lower it to the bottom of the test tube. And you should rapidly see bubbles start to form. And you can use the large stir bar in order to move the small stir bar around and cause the reaction to be stirred. So you'll rapidly see bubbles form, and pretty soon you will see the level of the burette drop. And you want to continuously lower the leveling bulb as you see this change. You don't have to do it every single ml, but as this starts to change, you want to keep these roughly in line with each other. Finally, you're going to have been stirring for a while. Eventually, you'll see no more bubbles formed. The volume won't change anymore. Then you want to get down at the level of burette and ensure that the leveling bulb and the burette are exactly the same level. At this point, you can measure your final volume. And then finally, measure the temperature of the leveling bulb. We'll assume that the temperature of the gas in this column will be the same as the temperature of the water in the leveling bulb. And here are some tips for success. As far as techniques, do not let the level of the water in your burette fall below the markings. So that would be on this. We don't want it to go down here below where there are markings, and if you follow the instructions from earlier, it shouldn't be a problem. Make sure your experimental setup is free of leaks. You would want me or one of your lab instructors to take a look at your setup before you do your first trial run. Make sure the water levels in your burette and leveling bulb are equal before the reaction occurs. Do not disconnect any tubing in your setup while there's still water at your burette. To remove the water from the system, you want to pour from the leveling bulb into the sink. If you remove the tubing, the water's going to go everywhere. So your procedure. So here's a shortcut for your procedure. Transfer exactly 3.00 mLs of H2O2 solution into your large test tube. Use a large stir bar to hold a petroleum jelly / yeast coated stir bar above the level of the H2O2 solution. Have your partner seal the system. Drop the small stir bar into the H2O2 solution and use the large stir bar to stir the solution. You will stop when the volume of the gas produced stops increasing. As far as waste, wipe the stir bar clean with a paper towel and dispose of it in the trash. Pour the solutions down the sink. Never return any unused reagent to the reagent bottle. This is particularly important for this lab. Lots of chemicals decompose hydrogen peroxide, and so if any contaminant made it into the bottle, the concentration of the hydrogen peroxide would be drastically changed. So here's some more tips. Get equipment to set up the gas collection apparatus. The large test tube should be in your drawer, and other items should be available in bins. See page 198, figure 1, for how to do the setup. Get one large and one small magnetic stir bar. Take care not to drop them down the drain when emptying the test tube at the end. Have your instructor check the apparatus for leaks. The lab instructor will sign the data sheet to verify that they've checked it for leaks. You'll use a 3.00 milliliter volumetric pipette to measure out the H2O2 solution. Apply a thin coating of petroleum jelly to the small magnet and then coat it in yeast. The density of the H2O2 solution, which you'll need for your calculations, is 1.01 grams per milliliter. The concentration of the H2O2 solution will be about 3.00 grams of H2O2 per 100 grams of solution. This may change slightly, and if it does, your lab instructor should record this on the board. Lab instructor will provide current barometric pressure in millimeters of mercury. Safety, everyone in the lab must wear goggles and lab coat the whole period. You can take a break in the hall from wearing goggles if you need to. Remember, again, wear goggles over your eyes, not on foreheads or chins. Anytime you're collecting gas in glass containers, there's a possibility of glass breakage. Glass tubing is easily broken, and you should be careful when connecting and disconnecting the rubber tubing. Waste and cleanup. All waste is flushed down the drain with water. Wash all glassware and return it to the appropriate locations. Use disinfectant and wipe down surfaces of your workstation.